Okay, well, good morning. My name is Seth Berman. I'm the Vice President of Engineering at Instantiations. And today I'm going to talk to you guys about security within VA Smalltalk. Now, there's actually two reasons I'm pretty excited to do this. One is we've got a lot of new great capability in VA Smalltalk. We've worked pretty hard on security. But really, independent of if you use VA Smalltalk or not, it's kind of a passion of mine, security, cryptography, and getting, especially students, aware of, real-world application development. This is a major hot issue, and if I think it's really important for application developers' careers. I think in the past, security has been kind of an afterthought, and it's something that some companies do really well, but sometimes not the companies you would expect. And if you read the news, every other day you see something about an email getting hacked, or your personal data being compromised on large companies. And so I would encourage you to really look into this field because it's a worthwhile field. It's not glamorous, but it really has a lot of high value, and we could use people who have knowledge in this area. So what I'm going to show is basically the security overview of what we got in VA. And we'll talk about some architectural goals of what we were trying to do. OpenSSL 1.1 capability, this just got released in September, and we are now compatible with that. And it was a major overhaul. I'll speak a little bit more about that. And then I'm going to talk about kind of the cryptography toolkit that we have, and just a little bit at the end about the SSL TLS connection support, HTTPS type of stuff, which most of us are familiar with. So this statement is rather obvious. Like I said, if you read the news at all, then you know this is true. It must be. Why is everybody screwing this up? But the reality is I wanted to break down a few issues with why maybe it's so hard. And so even cryptographers get this stuff wrong. That's one major thing. And how this shows up is kind of the worst of all is at the protocol level. So broken protocols like SSL, the poster child for broken protocol, which is Microsoft's point-to-point tunneling protocol, VPN, just horribly broken. And when you have a protocol breakage, what's so bad about this is that all implementations which faithfully implement the protocol are now wrong. And so SSL is a primary example of this. But we also have implementation-specific breakage. So I'm sure everybody's heard of Heartbleed. Well, so that was in the OpenSSL distribution. And so what this was a missing bounds check, and that's all it really took. And you could grab, an attacker could exploit, 65,000 some odd bytes of additional data, adjacent data in memory, which could be secret keys, and people's personal data. And it was considered by many to be one of the worst security vulnerabilities in the digital security age. Lastly, even if you get protocol right, you get the implementation correct, there are things like side channel attacks. So unlike a whiteboard, when you express cryptographic algorithms, when you express cryptographic algorithms on a computer, it leaves traces, things like cache behavior, things like equality checks, and we'll look at some of those. So when you look at the implementation, if you look for correctness, it's hard to visualize it in that way to say, well, it's not just algorithmically correct, but how is it actually behaving when it's carried out on a digital machine? So again, as I was saying to some of the students, this demand for security is only going up. So it's a worthwhile field of study. And so originally I gave this talk at ESUG, and so I was saying, our customers are receiving increasing pressure to provide higher security applications. But what struck me was, some of the other companies, CENTCOM gave some great talks that had touched upon some security capabilities that they've got coming in, as well as Jim Talk also talked about, encryption they're using for, I think it's transaction logs, something of that, one of those. So this is something we're all feeling in industry. This is something that our customers are demanding because their customers are saying, you must do this. So just to give you a little bit about what we had before we kind of did a whole overhaul. So we have bindings to OpenSSL, which is a popular SSL TLS implementation. About 2/3 of web servers run it. But it's kind of distributed in two parts. One is the cryptographic primitives, and these are all brought together to implement protocols like SSL TLS. And so that's another part to their distribution. So what we had was a binding, but it wasn't a binding to the cryptographic primitives, so those were not exposed. It was also very low level. So we have capability to bind to C libraries, but of course you're basically programming in C and a Smalltalk-like syntax, and you're facing all these issues therein. So we wanted to solve some of that. Furthermore, there was minimal test cases. And lastly, which is kind of interesting, is that the version of OpenSSL we actually distributed with the product was so old that it actually predated Heartbleed. So we could almost make a claim that we're not subject to Heartbleed.
But you're probably the moon of the previous thing worse.
Yes, well, granted. And so what we did in 8.6.2, this is our last release of the product, is we brought it up from, I think it was like 0.9.6, something really old, up to what was at the time the current stable level, the 1.0. There's basically three branches within that series. We also added some native memory management capability I'll speak a little more about. We introduced cryptographic primitives, and we've exposed that explicitly within the product. Lots of test cases, so we went and grabbed official test vectors from all these algorithms, and to make the check, just to check that by binding to OpenSSL and some of the stuff we were doing, we were still getting the correct results. And this one was really important to me, this last one. We have a whole application that just gives examples, executable examples of how to use every one of our cryptographic primitives. And and it's all just laid out in one big method, and it's kind of story-driven approach. So the comment will talk about Alice and Bob exchanging keys, this, that, or the other thing, and you can just follow it on down to see how to use, how this might be used. So what's coming up is, as I said, OpenSSL 1.1, a major revamp of the product, and we're talking about a post-Heartbleed response, where companies finally, in this sadly underfunded project with 2 part-time guys, all these companies started investing heavily in OpenSSL, and they've really turned this project around in a big way. So we've added that support. We've also, the API breakage is pretty large, but we've managed to hide that for the most part, and we've continued support for OpenSSL 1.0. Many new cryptographic algorithms we exposed. I'm going to talk about authenticated encryption and some key derivation algorithms, which I'll give a small use case so we won't go into any detail. And finally, the secure memory module. So this is for, you can think of customers like banks and insurance companies where actual in-memory representations of certain pieces of data need to be protected from process to process vulnerabilities or exploits. So I'll talk a little more about that. So some architectural goals of doing all this. Compatibility. That's always one of our major goals as a vendor. So what we did was we created the new cryptographic layer, and we slid it underneath our existing SSL TLS support. And so we did manage to maintain compatibility. And so we now support everything in the 1.0 branch plus 1.1. And for the most part, these differences, so customers have already built the systems on 1.0 APIs, and we have handled that, and I'll show how. Separation of concerns, this is kind of an obvious thing that you'd want to do, but just to kind of talk about how we split things up. So we have our API objects. These are kind of you can think of like a key derivation algorithm or a cipher or something like this. But separate from that, we have our dispatching engine. So this is going to be the thing that interacts with OpenSSL, makes OpenSSL calls. And this is actually a big piece because we do some special things here. And finally, we do have a native memory management system, which goes kind of beyond just weak collections. We do some other things based for pointer tracking, and as well as OpenSSL itself has some different way. It has internal reference tracking, so we need to stay in sync with what they're doing. So with performance, we have all OpenSSL calls are made on native threads. So we have asynchronous call out. So essentially, the Smalltalk process will make a call using a native thread. That Smalltalk process will be blocked. Other Smalltalk processes may continue, and they in turn may make native calls. So in order to handle this, you need thread locking implementation. So before OpenSSL 1.1, you had to provide your own. They did not provide thread locking. So they just had kind of an API you had to hook into. So we have that, but we detect if it's 1.1, we no longer need to do anything. And so this allows for usage of multiple cores. So for example, I've done some encryption, decryption, where I can push on my i7, 5, 6 threads of execution. And really the bottlenecks are either the thread locking or the random number generation of the machine. So in safety, we use, so like I said, I keep coming back to this native memory manager. So kind of the normal, we have a Smalltalk GC notifier. So once this object, which is kind of pointing to native memory, is getting garbage collected, then we'll get a trigger on that. And so we'll make sure that it was freed if it wasn't explicitly freed. Now, in order to prevent things like double freeing, we actually have memory ownership. Each API object has the concept of memory ownership. And it knows how many reference counts it has. So it stays in sync with OpenSSL's internal reference counting. So in other words, you can't say, free, and get, undefined behavior because you're freeing garbage, essentially. And we also have kind of specialized back pointers. So we keep track of every pointer, and then if you make copies of that, those copies know who the primary pointer is. So they're kind of weak references that know who their parent reference is. So when you have a lot of copies out in the system, it always knows which is the one that needs to really be freed. So we kind of just have this large system where we make sure folks don't get in trouble. So, and I'm talking a lot of complexity here, but the reality is when you use the API objects, you don't need to know the details really about any of this. So with OpenSSL 1.1, it was a major revamp, post-Heartbleed, and when I brought this up at ESUG, it was still in beta, so I was having to say, well, I hope by the time we release that it'll actually be, OpenSSL itself will have been released. And thankfully at this point, about a month later, it was released. So, and I got kind of scared because I ran my test suite against the newest version, and they had made one small change in one of the bit-oriented ciphers where they basically interpreted the incoming argument as bits in size versus bytes. And so when I was running my test suite, I got GPFs all of a sudden. I'd been running the thing for months and months, and then all of a sudden, I get this. So thankfully, that got caught because they made a late breaking change. So leading up to that, with all the good comes the bad for us, which is API breaking. So what we do is, so this is a native binding. So we have pieces of the product that describe the structure layouts of OpenSSL, and from version to version, some of these things may change. And in fact, in OpenSSL 1.1, most of these structures are now opaque, so they have mostly getters and setters. You don't actually need to know the internal memory representation. So once you load up a binding and it connects to the binding, it detects the version and it readapts everything in the whole crypto and SSL library to match what the memory layout of the DLL you're binding to. And finally, we have a lot of version fallback logic. What this means is there was so much API breakage that basically, if you're in 1.1, there may have been some things that were new, and so basically we had to do some version detection to kind of emulate behavior. Now this is kind of high-level behavior, not cryptographic algorithm stuff, but we just have a lot of things in place to make sure 1.0 and 1.1 are compatible, and it's pretty much transparent to the user. And but this last point is important. And so it says we don't actually implement algorithms in Smalltalk, and this is very important. So again, our implementation may be correct from our what we're seeing, but there's observable cache behavior or CPU behavior or other types of things that we may not be able to count on, especially running on a virtual machine. So our semantics. So this last one's a key point. Say you're computed, you have a hash that got computed, and you're comparing it against a stored hash. Well, you got to make sure that you use constant time equality, because if you use some sort of short-circuiting equality, then that actually leaks information about how close these guys are. And so that's just an example right there. I mean, you're looking at your code, you're using Smalltalk equals, and you can get a sense of how much detail you have to think in when you're implementing these algorithms. Okay, so I'm just going to go over the cryptographic library, and again, I think this is just good for folks to just get a sense of, this is almost the full gambit of what you'll see in any cryptography toolkit. And I'm not going to talk in any great detail about them, but it's important to know that it's more than just HTTPS connections today. Companies do a lot more with this stuff, with data at rest and data in flight. And these are the algorithms that help. So with secure memory, again, this is for folks with higher threat models. So this is like banks and insurance companies. And basically you want to protect data that's in memory. And so this is intended for really long-running servers that have keys sitting there in memory. So we have special objects we call secure objects, and they're essentially wrappers around external data, but they have special APIs. So for example, they won't print themselves out because you might accidentally log this thing, and you don't want to log the memory address of this thing. Or there's other special facilities like that we'll talk about. So there's actually multiple. There's a couple of different ways that we implement this. So OpenSSL 1.1 provides what's called secure arenas. And so what we're trying to do here is prevent sensitive data that's sitting in memory from paging to disk. And so, and another thing is, if the core dump occurred, you don't want it to show up in a core dump. So how you accomplish this on many platforms is that you have a special section of the heap which is kind of page guarded from either side, because you have to think about like Heartbleed, buffer overruns, wandering pointers coming in from either side. So if it hits one of these page guards, then that will segfault. And so those are called secure arenas, and that's what we have for Unix and Linux. However, on Windows, we don't have. Well, it's actually a question of debate: is can you really pin processes to memory, and it depends on what version of Windows you're talking about. So we actually went a slightly different direction because secure arenas were not implemented in OpenSSL 1.1 for Windows. So what we did is we said, okay, well, rather than trying to prevent it from going to disk, what we're going to do instead is just make sure it's encrypted in memory for the maximum amount of time that we can actually do it. So that means if it does page to disk, it'll be encrypted. So to do this, we use some Windows APIs from Microsoft's Crypto API. So the encryption key is actually per user generated on boot by Windows. And this key is stored in kind of a special section of kernel memory that's kind of non-paged. And by default, we have it set up so only the VAST process itself can actually decrypt. So the OpenSSL dispatcher, so it gets kind of complicated here with multiple threads of execution going on, will decrypt the incoming arguments intended for an OpenSSL function. But it also has to keep track of how many times it's inside an OpenSSL function. So it'll then call the function and it'll re-encrypt on the way out if it's not still within another function call, because we got multiple threads of execution going on here. And so the window of time that this thing is decrypted is for the duration of that call, well, kind of in synchronous mode. You can think it can expand a little bit with multiple threads going at the same time. But so that's kind of what we have it down to. We have a streaming library where, so this is for really high performance OpenSSL streams. So you can think about, you can be pulling data in from sockets, from files, and then you're setting up a bunch of filters, like a pipeline of filters that this data is kind of transforming as it flows through, and then it will end up, in memory or whatnot. So you can chain them together to create these crypto pipelines, and I have an example here at the bottom, and that's exactly the syntax. We kind of overload the OR operator to act more like a Unix pipe operator. So so in this example, what we have is, first you start off with a buffer. So basically, if you write to that buffer, the data is going to be buffered up. That's going to flow into a SHA-512 hash. So that bio, the SHA-512, will be constantly computing a hash of the data that's flowing through it. That will flow into an AES-256 symmetric cipher, which will encrypt that data. So now on the way out, it goes into base 64, which will base 64 encode that data, and then that will flow into a file. And so to reverse this, it's pretty simple. Instead of writing to the buffer bio, you read from it. So when you read from the buffer, you can imagine kind of flows all the way down. You're now reading from a file that gets base 64 decoded, then it gets decrypted. The hash is computed on that decrypted data, and you're reading it from a buffered piece of data. As far as what we offer, we've got, this is the general stuff you'll find in a crypto toolkit. So we've got message digest, just a whole host of them. And you can kind of see at the bottom an example of, you've probably seen this before in other places. It's, you've got this kind of factory object like a digest, and you're asking for a specific kind, and then you're saying, yeah, give me the printable digest for some sequence of bytes, and it will produce the digest. So this is for data integrity. And so MACs are data integrity, but they add authenticity as well. So we've got a couple of algorithms that came in, HMAC and CMAC. So one is digest-based, one's symmetric cipher-based. And so you can kind of see you're doing the same thing, but you got to add a secret key that you're kind of using. Some symmetric ciphers. So this is for encryption, so this has confidentiality. So we have a shared secret key here. We have lots of different kinds of ciphers, as you can see. What's new, what's coming up is authenticated encryption. And so with unauthenticated encryption, what we had before, this is only good for passive attackers. So it cannot detect the fact that you are, let's say you see a bunch of packets coming through and you're fiddling with the bits on some of the packets, or you're injecting new packets. Unauthenticated encryption can't really help with that. So authenticated modes, and in fact, what's been done historically, although wrong in lots of cases, is that you use an unauthenticated mode of encryption, and then you use a MAC. You MAC over that data to get the authenticity, so you can detect changes. Unfortunately, a lot of protocols got this wrong. So SSL got it wrong, SSH got it wrong, IPsec got it right. So there's a few ways, Are you macking the decrypted versus the encrypted? Sometimes, let's say you're building up a packet and you encrypt some data, and that data has a length of a certain kind, and you append that, and then let's say that you mac that encrypted data and you append that. So now you've got everything except that you forgot to mac the length. So now somebody can actually change that length, forcing you to overread. So you got to be sure to include everything in the mac. So this got really hard. This got really hard for folks because they were just doing it wrong. So somewhere around 2010, we started seeing a lot more authenticated encryption modes which handle all these issues. The best one I would recommend, which it used to be covered by patents, so it wasn't in OpenSSL. But OCB is a one-pass algorithm it's as fast as any unauthenticated encryption mode. So,
are these mode implemented in Smalltalk or pushed to SSL?
Oh yeah, that's a good point. So all the cryptographic algorithms for everything is in OpenSSL. We don't implement any algorithms. So here's just a small example. Again, you'll kind of see the same pattern: a factory object, and you're asking for a specific kind of cipher, and you're encrypting the data. The tag data is basically the authentication tag, so you can detect if this stuff changes, and then you decrypt it. Public-private key, this is kind of a huge field. I don't really want to spend too much detail on it, but we've got public-private key, RSA, DSA, Diffie-Hellman. I hope to get elliptical curve crypto in the next version. So this is one of the new ones that wasn't in the previous iteration. So this is key derivation algorithms. So, and believe it or not, you actually know what these are, and maybe you already know, but so for example, PBKDF2, this is password-based encryption. And if you've ever heard of LastPass, 1Password, KeyPass, any of these password managers, this is the algorithm that they all use. And essentially, it's meant to take low entropy keys, something that's is cryptographically weak, and so that's going to be something like a human-generated password. People suck at creating passwords. And even if they think it's a strong password, cryptographically, it's not. So you basically, these algorithms take cryptographically weak key material and turn it into cryptographically strong key material. But it also does it very slowly. It's intended to be a very slow algorithm on purpose, and that's for brute force attacks against it. So in PBKDF2, this is a very CPU intensive with a dial on it, so you can dial it up to make it take a full second or 2 seconds to do an actual derivation of a key. And so this was fine, but then folks were, hardware's really cheap now, so folks were going out buying custom ASIC boards or GPUs, sticking them together and launching, parallel attacks against PBKDF2. So they had new algorithms such as scrypt come out. So this is not just CPU hard, this is also a memory hard algorithm. So you can dial up the memory to be, 1 gig, which means if you were to do a key derivation, you would need 1 gig of memory. And typically, integrated types of hardware don't have that kind of memory available. And of course, it's a moving target. So, as hardware advances and gets more memory and more CPU power, the dials here have to change. And just HKDF is kind of used internally in a lot of algorithms. It's not a password-based algorithm, though. So the key material, that's the input key material, needs to be very high entropy. So another example we kind of see in bold there, the factory object. I'm asking for scrypt. I give it a key length that I want, and I send in a really poor password and have it derive, I send it some values and have it derive a really strong password. So actually what you can see these memory parameters here, or CPU and memory parameters. This is the kind of stuff you're going to end up storing in the database when you want to authenticate a user or something like that. Okay, And this is just reading it, verifying a password. So the last part of this is important. Again, I say we strayed from implementing any sort. We want to stay out of the algorithm business when it comes to cryptography. But the fact is, with the verify, we're verifying a password with a hash. So this is one area where, to make extra sure that we're using constant time comparisons here, which OpenSSL has the functions for. But if I accidentally use smalltalk equals, then this would have basically taken everything and it would have ruined it. So always have to be extremely careful. And one thing I want to point out, I think Leandro asked about this, and it was a good point that in these examples I'm using string literals for the password. And in reality, you probably don't want to do that. Well, in the case of string literals, you can't zero that out. But also so typically when I use keys, I actually ask for either native memory or I ask for something. So in VA, we have a kind of a fixed space where things don't move. Because the garbage collector is basically going to, if you use a password that you have sitting there in memory, the garbage collector, either a scab, some sort of copy collector, putting stuff on the free list, compaction, it's just going to end up, for efficiencies, it moves things around and it doesn't zero out the previous stuff. So this is again higher threat models, but this is a reality. So you imagine things get core dumped or some sort of memory inspection. That's just a reality of garbage collectors. So typically when I create keys, I don't create things like what you see here for brevity.
Have you thought on adding support for secure objects to the VM? So the GC solves that for you?
Actually, no, I haven't considered that at all.
Yeah, this is a thing which came to mind is modifying the system so that if a particular class of object would only be allocated in old space.
Mm-hmm.
And because it's in old space, we use computers, and it would be tagged by something that would say 0 it out on the
Yeah, so that last part is good. I mean, what we can do now is allocate from fixed space. And so then we can, but like you said, I mean, we also have to remember to manually zero it. Whereas you're saying that...
Worse, you have to expect the programmer to do it and communicate to the programmer through profiling, right, that there's a particular cost.
Right.
But I love your example, your use of the method as the story, and that's an excellent place to embed that kind of information.
Yeah, that's right.
I'm very interested in actually seeing that method and in that as a whole being expanded upon.
Yeah.
It's a very natural way of doing things. It's related to tests.
Yeah, that's a good point. Okay, so I'm kind of at the end of this last slide. I mean, SSL, TLS, this is probably the stuff we're all kind of familiar with the support for HTTPS connections. So these are the algorithms for that. And the only interesting thing here is all the cryptographic primitives I just showed you are brought together to implement SSL, TLS. So all you really got to do is, if you're familiar with those primitives, you just go read the spec and you'll basically understand how things are fitting together. So we've gained support for the latest version of TLS, and as I've already said, OpenSSL 1.1 as well. And really all that memory management, everything else I talked about in the crypto layer is inherited. I mean, it's basically SSL, TLS gets the same functionality. And that is the end of my presentation. Thank you. Thanks.
For the cryptographic schemes where you were piping stuff together, did you take a look at did you consider being compatible with the Extremes library?
No, that actually probably would have been good. If we had Extremes, that would be. I don't think I've seen a version of Extremes for us. But you just mean in terms of API interface.
I don't know if the port has been made. It's just a fairly clean open source library, which I happen to be in the process of porting to Genesect.
Okay.
It would be kind of nice to have multi-dialects out of nowhere there.
Yes, I did not consider that.